Okay, everybody, how's it going? We good? We're ready? Okay, were the notes up? Were you able to see them? Okay, if anyone is viewing online, or if you have a friend who's viewing online and cannot hear the audio, please let me know. Or if you could let me know, because I've now had two misfires with the issue. Okay? Or with the issue, with YouTube Live. So hopefully this time they can hear us, and hopefully this time it works. When I was walking in, we had a request to go over one of the homework problems. Okay, so the question in hand, it's not this. The question is, what was the elongation in the middle member? Right, and that's that's the orange one. And yeah, I know the colors are not great for everybody. Okay, so what we need to do is figure out what the force is in that member, right? So what I suggest is that we do a cut. Just like this. There's an F3 there. I don't think I really need to do this. F2 there, right? And I do equilibrium. So let's just say I'll call it Fi, F internal. Okay? So what is the equation? The equilibrium equation, right? So I have, if I'm defining this as positive x, then we have our F3 minus F2 minus Fi equals 0. So that means that the Fi is just equal to F3 minus F2. Okay? And they want to know the elongation of this middle member. Well, we have a spring constant given for us, right? So we know that F equals K delta, right? So if I want to know delta 2, all right, I just need to know Fi over K2. All right, so that's how you would go about solving this particular problem. Any questions on this? So when we're doing deformation, right, we need to make sure that we're performing equilibrium. And if you want, go back to the notes on, I think it was session 2 where we did static equilibrium. And we first want to look at external equilibrium on the system. Okay, and then we do a cut. In this case, okay, I went ahead and I just went right at it. I mean, we have this is an external force, this is an external force, but I'm able to do a cut. If you wanted to go about it and go and leave the right side exposed, okay? So let's just say that you wanted to, let me get some more space. If you want to have the right side exposed, and I'll just be kind of quick here. So I think F3 is this direction. F2 is this direction, and F1 is this direction. Okay, if I was like, oh, you know what? I really rather have this setup. And that's the internal, right? If that's what we want, then I got to do something on the wall. That's a case where we would benefit from first doing the external equilibrium, right? So what you would do first, or what we might do, and maybe I'm being a little loose with the order here, right? But this would be for external equilibrium. Right, so I'm just going to call it F wall. Okay, so here when we do, and let's again say this is plus x. So when we do the summation of the forces in the x direction equal to 0, what are we going to have? We're going to have F3 minus F2 plus F1, okay? And we've got it, we got minus F wall. And that's going to be equal to 0. So in this case, F wall, right, will be equal to F3 minus F2 plus F1. So now when I go ahead and I look at my cut, okay, right, Fi is just going to be, well, let's do it nicely. Let's do Fi plus F1 minus F wall equals 0. Okay, so we plug in what we have here, Fi plus F1. That's going to give us a yeah, I gotta take it easy, right? F1 and F1, they knock out. Fi once again is equal to F3 minus F2, and the delta is once again going to be the F3 minus F2 over K2. Okay. Any questions on that? So it's good that we're having these questions and these discussions, and I'm glad that we had a session on equilibrium to try to go at some of these issues. And so if you have other questions, just let me know. All right. Cool. Should we move on to today's session then? Yeah. All right. So today is going to be fun, maybe. All right, we'll see. It's an opportunity to link our loads and internal loads in terms of forces to stresses that allow us to think about different configurations, but then understand at any location in those different configurations what the material is feeling. All right, I know we don't think about materials as having feelings, okay? But we want to get an idea of how local regions of our materials are behaving. And the powerful thing about using stress is that I can take a material, and we'll have a whole session on material testing and selection and things of that nature. Actually, we're going to talk about materials probably for 2 sessions. I can take a material in the lab, I can stretch it, and then I can say, oh, it's experiencing this behavior. It's feeling this amount of stress. And if I cause it to feel too much of that stress, then it will yield or it will fail. So I now understand how the material behaves. I want to build a big structure, or I've already built a big structure. I'm not going to take that whole big structure, which is a building, and stick it in a material testing machine, right? That's not an option, not feasible. Although we at Rutgers do have some people in civil engineering who make some pretty awesome, huge testing equipment for bridges, okay? But the idea is I can use what I know about equilibrium. I can use now what I know about indeterminate systems, right, to figure out what the internal loading is going to be in this huge, big, awesome structure, and then relate it back to that testing that I did on the small sample of the material to be able to know whether or not it's going to fail, okay? That's the power of being able to calculate stresses. And it's good to know how much things deflect too. So strain is important as well. Okay. So let's go ahead and look at what we're going to do today. We're going to, just do a brief review. We actually kind of already did a brief review of axial loading, okay, from the third session, just one slide. And then we're going to talk about the different types of stresses. And I think some of you said that when you were in statics that you did have a chance to look at stress and strain. So some of this is going to be review. And then I think also, there may be a couple twists, and this may be a little bit more mathematically rooted than what you've seen previously. Okay? Maybe not. We'll see. But not all the way. If you want to really get into constitutive equations and the mechanics of things, go to grad school. Okay? But we're gonna get a little bit deep. Not too deep, but a little bit. So last time we discussed axial loading. We discussed how we could think about Hooke's law, both for mechanical springs and for bars. We looked at how we could do superposition. And then we also treated some problems with indeterminate axial loading. Okay? And we looked at how we could use geometric compatibility as one technique, or use superposition with geometric compatibility, in fact. All right? We still care about the geometry and being able to put a restoring force on it to be able to get, in the simple case, get the displacement back to zero. So we still care about geometry. So today, let's talk about stress and strain. And I realize now that my headings are not the awesomest, because this says stress, and then I could have bumped out strain because they're not the same. Anyway, but we're going to go through normal stress. We're going to go through stress, normal strain, shear stress, shear strain, and then stress tensors. So we can describe a resultant force or moment internally on a structure. Okay? So for example, we have these balls, but they're overlapping, okay? And then we take a slice and we look at the internal picture on that slice. We have a force, an internal force, and we've drawn these internal forces many times with axial loading, right? We just did went through a whole series of things. We did beams, we did trusses, right? So we have an idea. This is an internal force. Now, it's interesting to note that this internal force needs to be internal. Okay? So on a surface, okay, if I do a cut right there, right, and I look at the air, for our intents and purposes, the air is stress-free. Okay? So there's some, you can think about, there's maybe some interesting behavior happening at these discontinuities, and in fact we do have kind of edge effects and things that often happen near the surfaces. But for our intents and purposes, again, we're going to be looking inside the material, and inside you could have some type of resultant force, some type of resultant moment. What is the origin, or what are the origins of these resultant forces or moments? Well, they are from external loads, the distribution of loads that have been applied. And we might want to think about looking at the distribution of internal forces, all right, individually as a bunch of kind of mini forces, shall we say? We're talking stresses essentially, distributed on that surface on which the internal force is acting. Okay. So Hibbler, all right, more or less is saying that stress is the quotient of a small force acting over a small area. Okay. All right. And the intensity of internal force acting on a specific plane or area passing through a point. So it's at a location. Okay, so there's our location in this case. When we cut beams later, we will see how location matters. Okay? It's like real estate. Location, location, location. Okay? Where you are matters in the internal structure. Another definition. Stress is defined as the force across a small boundary per unit area of that boundary for all orientations of the boundary. Okay, so in this case, you see that this force and then these resulting stresses, or you could think of them as stresses, or you can look at them at DFs. All right, they have different units. All right, so but the arrows could be thought of as either. Right, so when I say DFs, I mean like small pieces of the force. Or it could be small pieces of the force divided by the small area there, right? As we've just been talking about. They don't necessarily have to be orthogonal. They don't have to be coming out normal of that surface. Now that's kind of a bummer, right? Because we like it when they come out normally. But even today, we're going to talk about shear stress, right? And shear stress is when it's not normal, but it's actually tangent or parallel to that surface. I clicked on the link. It's the slide. Stress is the force per unit area on a body that tends to cause it to change shape. All right, so this is connected to strain, essentially. If there are internal stresses, if there are internal loads, and this material is not perfectly rigid, we expect that there's going to be some change in shape as well. So here, let's say that this is a little delta area. And we're defining a coordinate system, x, y, z. So let's say that x and y are in the cut, in the slice, okay? And we'll say that z is coming out normal, okay, to them. And this is a right-hand system, right? 1, 2, 3, all right? So, and then we have these delta f's, all right? These delta f's over these small areas. Okay. So, if we take this plane and now we put it sideways, all right? And let's just say that this big squarish looking thing is the kind of overall area, and we've now focused in on one of these delta A's. Okay, so what you have is this delta AZ. Now, the areas, okay, that we select on a surface that we've cut, they always have to be orthogonal. Okay, right? You remember like calculus, multivariable calculus, whatever, the n hat, right? Right? It's got to be coming out. So delta AZ is just saying, hey, this has got this z is normal to this area. But delta F, like we said just a second ago, doesn't have to be in the same direction as Z. Now, it can be an arbitrary direction. So if this vector, delta F, is an arbitrary direction, I can still break it up, or not if. I can use Cartesian coordinates and I can break up that delta F, that vector, into 3 components, right? And that will give me this resultant force vector. So in this case, we make it kind of easy for ourselves. We say, all right, we're going to have a component in the x direction, a component in the y direction, a component in the z direction. And I can map out the sum of these vectors to get the delta. To get the delta F. Now, I can define another vector called the traction vector. Okay? Now, the traction vector is collinear with the delta F, but it's just scaled essentially. Right? Remember, we're talking about stress. And what are we scaling by? We're scaling by the area. Okay? So, in this case, I drew the traction vector to have, it's just a scaling thing, right? I would have to have a different coordinate system or a different set of units to describe it, because now this traction vector is going to be describing things not in terms of newtons or in terms of a force, but it's going to be describing them in terms of a force per unit area, or maybe newtons per meter squared. Note the traction vector, like we were discussing before, it's coming out of this surface on this side, right? But these vectors that we're discussing, these stresses that we're discussing, they can only exist internally. So this is just a note to say, hey, for every action, there's an equal and opposite reaction. Okay, so if this traction vector is coming out of P on this side, right, it's going to be coming out of P on the other surface as well. And they're going to be in opposite directions. And we've kind of gotten familiar with that, right? As we've been doing our internal cuts, exposing the right or exposing the left, okay, we've gotten kind of familiar that there can be these opposite vectors of force with each other. Okay, so this is just copying exactly what we just had, okay, and we're going to go a little bit deeper. Maybe, right, we want to break the traction vector up into individual components as well, because I like Cartesian coordinates. I like polar coordinates too, kind of. Spherical coordinates, if I have to. Normal tangential components, also if I have to, okay? So let's break this traction vector into components in the I, j, and k directions. And when we do that, we remember, there's these quotients of small forces acting over small areas. That looks like it fits the bill, or these three look like they fit the bill. And so we are going to assign some sigmas. Okay, sigma is what we use to designate stress. And let's talk about what these stresses look like and what their subscripts mean. Okay, so we've got a sigma zx, a sigma zy, and a sigma zz. And I haven't put out exactly, but if you're looking at the complete notes, you know already. There's a convention here. Not like we're all getting together to have a fun time, but like a notational convention. Okay. What do you guys say? For those who haven't looked at the notes, what does it look like the convention might be? Yes. Yeah. Okay. So we're looking at the direction of the area as the first index, okay, and the direction of the force as the second one. Okay. So if we have everything coming out of the z, right, that means that all of these three, which you already see over here, right, they're going to have the first index of being a z. Okay? And this one is acting in the zz, all right, or it's acting in the z direction, right? So this one's going to be sigma zz. All right, this one is acting in the x direction, so it's going to be sigma zx, and this one's going to be acting in the y direction, so sigma zy. So this traction vector can now be written as essentially a combination of stresses multiplied by appropriate unit vectors. And the convention, as we've just mentioned, can be thought of as having the first subscript specifying the direction of the face of the area, while the second subscript is describing the direction of the stress or the force. Any questions on this? Yes? Okay, so what we can say is that we can come up with a linear combination of stresses that will give you the resultant force divided by area. Okay.
The t vector itself, that's not always going to be in the direction of, say, the delta f vector?
It will be in the direction. It will be in the direction of the delta F. Okay. Good. Good questions. Good clarifying points. Okay, and just, yes, a note here that when I said sigma sub ij, that doesn't mean that they're I hat, j hat. Okay. I could have done sigma sub AB, but I was like, that's not really what people. If you look in the mechanics notes, and typically they're using i's and j's. They're not using, you know, x and y. And x and y would be confusing, right? I could have done m and n. Yeah, that would have been okay probably. So let's talk about normal stress. We already discussed kind of what the definition of a stress is. Now we'll talk about simple stresses. So in some situations, the stress within a body may adequately be described by a single number or by a single vector. Okay? 3 such simple situations that are often encountered in engineering design are the uniaxial normal stress, the simple shear stress, and the isotropic normal stress. And we will cover these other ones. We will cover shear stress today, all right? But I didn't get I'm behind. I didn't get as much done as I wanted. Okay, I wanted us to talk more about shear. I wanted us to talk more about shear. Okay, but we'll have time. We'll get to it. Okay. But uniaxial normal stress essentially is saying, hey, if this is one of those cases where just give me essentially a scalar. One scalar will do. Right? And in this case, that scalar is going to be the stress acting normal to the selected face. Right? So which one of these is doing that? Sigma ZZ. So this is normal stress. And we typically do not write sigma ZZ because that is repetitive. We just write sigma Z. Okay? Or we don't write sigma XX, we just write sigma X. We don't write sigma YY, you just write sigma Y. So now, what we have here is a 3D element, right? So we were looking at just a plane, right? We had said, we're going to just look at some plane in the z direction. And that was supposed to be on the surface that we had sliced or cut. Now we're going to go back and say, hey, you know what? I think that plane that you had could actually be part of a cube. Okay, and we're going to spend some time thinking about what is the state of stress at a point in a structure. And when we do that, it's not just one plane, okay, of the point, if that makes any sense. We're going to be looking at essentially points or cubes that we put at points in structures. Okay. So here you go. This is X, Y, Z. It's a cube, right? So the face that we've been thinking about has been this one, this right face, okay, with the Z coming out. So if now we begin to think about normal stresses, sigma X, sigma Y, sigma Z, and we have a Z direction, a Y direction, and an X direction, right? We can stick little stress vectors out of these surfaces. So this would be the sigma X, this would be the sigma Y, and this would be the sigma Z. Now, when we think about equilibrium, sometimes we take a shortcut and we say, we're just going to make the stresses equal and opposite to each other, and everything's going to be great. That can be dangerous, okay? Newton's laws apply to forces and moments. Okay. So what we want to make sure we're doing is that we know what the forces are that are balancing out with each other for them to sum to be equal to 0. So we already discussed this is the convention. All right. Let's look at equilibrium. Look at this. Or maybe I'll go back. Look at this. If you just took a cube, all right, and you put a force, all right, and in this case, it's a stress times dAx, right? Sigma x dAx is going to give you the force on that face. Which direction is this cube going to travel? It's going to accelerate upward, right? If I put a force over here, sigma z, it's going to accelerate in that direction. And if I put a force over here, right, it's going to accelerate toward me. So for us to get equilibrium, right, maybe we need to put some additional forces on this cube so that it doesn't accelerate, so that the sum of the forces is equal to 0. So you get where this is going. It's an incomplete picture to only have the orange stresses here. Okay, now, am I always going to draw all 6 of these normal stresses? Maybe not. Okay, but it's important to realize that we have opposing stresses that are associated with their positive counterparts. Now, a little bit more on the convention. This face is the positive z face. This face is the positive y face. This is the positive x face. What's this face over here? We actually are going to call that the minus z face. Okay? Because if z is positive this way, it's actually going in. All right? And so this normal is in the minus z direction. This normal here is in the minus x direction. This normal on the back face that we can't see is in the minus y direction. Okay. So this is to help us with the convention. So if I want my opposing stresses, or the opposing forces associated with these stresses acting over these small areas, if we want to keep things really straight, we should say that this is a stress, this one down here, is a stress acting on the minus x face in the minus x direction. Okay? Sigma minus x minus x. Okay? Sigma minus y, sigma minus z. Okay? This is if this is like, we want to do really precise accounting. But look, is there any other force in the vertical direction? No. Is there any other force in the y direction? Is there any other force in the horizontal z direction? No. Okay? So you're not going to see people write this. Okay? Instead, we're just going to say, hey, this sigma x, it's sigma y, it's sigma z. Okay? But note, just note in your brain that it's really a minus z face and a minus z direction is equal to sigma z, for example. So here's a convention. We define the resulting stress component to be positive when a positively directed force component acts on a positive face. Alternatively, a positive stress component results when a negatively directed force component acts on a negative face. By a consideration of action and reaction, we see that the definition follows from the first. When a force component acts on a positive face, the resultant stress component will be negative. So in addition to saying that, okay, sigma minus z is equal to sigma z, when I draw it coming out of the face, right? If you have a vector describing a stress that's going into a face, that's going to be negative. Okay? So now you're like, oh yeah, compression and tension. I got to have some way to express it, right? Because we've known in the past, you have a positive force coming out of the face, that's a tensile, that's a tensile force, right? It's in tension. Tensile loading can kind of go back and forth, right? Like it's like, okay, it's in the line, right? So you got to be a little bit careful, but if you say compression, people know what's going on. It's the opposite direction. Okay, so where did I go? All right. Sorry, I didn't mean to. I meant to those just magically appear, but they didn't. So now we have a little bit more. So force on AX due to sigma x, as we mentioned, is Fx is equal to integral of sigma x dAx. All right. So this is an important relationship to have in mind too. Okay. Imagine you have a cut. So it's a little bit weird because we're kind of going back and forth between saying, okay, this is a point and it's infinitesimally small, and this is a really small surface. All right. And hey, I just cut your bar and have an exposed surface, and I have a stress coming out of it, and I have an area. And if I integrate that stress, distribution of stress, that profile of stress on the area, I can get the overall force. Okay? So it's true at the small kind of, microscopic level, for lack of a better word coming to my head, and it's true at the macro scale when you have that surface. And you can see that, yes, these things are going to be in equilibrium. Okay? And equilibrium applies to the 3 pairs, right, on the 6 faces. So let's do an example. What are the normal stresses in the 2 sections of this bar with an axial force? Okay, so we've seen this problem before. Sorry, we're drawing here. Okay, is this a determinate or indeterminate problem? Of course. Determinate or indeterminate? Yeah, determinate, right? There's not a wall there. We have one internal force we're looking at a time, and that's equal to the reaction force. And so one equation, one unknown, boom. Okay? So we don't have to worry about using compatibility or superposition plus compatibility to figure out what the internal forces are. But if we want to figure out what the normal stresses in the 2 sections of this bar are, right, we at least need to write out what the forces are inside them. So we can do external equilibrium first. That's our first kind of go-to thing to do. And I have nothing on the right side, but yes, we have a wall. Okay, reaction force on the left. And we do the summation, and we figure out that, yes, the reaction on the wall is equal to this force that's being applied there. And then we do the internal equilibrium, and we notice, okay, so this is like a slice maybe right around here for the first section, right? So the 2 sections, I know there's a K1 and a K2. Are we going to use K1 and K2 here? No, but I copied it from another problem we did last time. So figuring out what this internal force is just saying, hey, this Fx is equal to the F, right? We just did a whole loop-de-doop to get to what would have, been a pretty, and if you know the answer, don't spend all the time to do this, all right? But, it's good to know where these things come from. So here, again, if you know the answer, right, this portion is just along for the ride, so we know it's going to be equal to 0. But once again, we can do the equilibrium out, and we get that Fx is in fact equal to 0. Okay, so this one's easy. This is straightforward. Okay? Now, if I look at the bar in a slightly crude 3D drawing, okay, that I've made here, I know that I don't have enough. I probably, if a better worded problem would be with cross-sectional area A. Okay, but here we're adding the A right now. So here's the AX, here's the FX, what is the sigma x going to be equal to? It's going to be equal to just fx over ax. And fx is equal to f. Right? And for region 2, we can add a little bit more to this beam right here, okay? And this could be, you know, this, I guess if I'd been more like, I could have made these squigglies, all right? So you know that they're internal cuts. And for this second region, sigma x is going to be equal to fx over ax, but fx in this case is equal to 0. Okay. So fx, ax, these are normal stresses. F is acting in the same direction as A. And as a general rule, it's just match the indices and take the quotient. Yes? Oh, okay. Yeah, sure. Sorry. Yeah, sure. Thank you for speaking up. That is one disadvantage of having things, of trying to line things up right here. It's like it's kind of ready to go, but yet I'm losing connection with how fast or how slow it is to how long it takes to write. But while you're, so are there any questions on this? Because this problem is pretty much done. There's just one little extra note I'll throw in there in a second, but are there any questions on this? Do you think that calculating the internal force will be the hard part of the problem or the easy part of the problem when you're trying to calculate internal normal stresses or normal stresses? To say that equilibrium is actually, you know, the calculating what that internal force is typically going to be the harder part. Okay. Now we will, in some cases, when we, at least in bars, right? Because like you maybe have to do equilibrium on a whole truss system, right, to figure out what the internal force is, and then it's like, okay, that's normal stress. Boom, that's right. So being able to handle the equilibrium portion of these problems is extremely important. And usually, right, we reward credit appropriately, right? So if it's hard to do the force part, right, and the stress part is like, you know, easy, then that's going to be a few points. But we will get to systems where we essentially bypass. We go like from moments to stresses, okay, or we go from torques to stresses, right? Where we kind of, how do you say it? We don't exactly, yeah, there are going to be some expressions that kind of get us right to stresses pretty quickly, okay? And in that case, yeah, it's just the whole thing is going to be hard because you got to figure out what the appropriate factors are to get to the stresses, okay? The last little note that we're adding here, that this force is often either uniform across the bar, okay? Remember, we're talking about kind of points, right, on a surface, okay? So this force is somehow, excuse me, being distributed uniformly, or we're taking an average, okay, on when we're calculating this stuff out. So you could see systems where, okay, you have a resultant force, right? For example, when we do beam bending, okay, we're going to have, I thought it was this shear force, okay. You know, I thought it was this or this bending moment. But like a shear force on a beam, like remember, you know, when I'm talking about, I draw the V down, you know, all that kind of stuff I solve for it. That's like an average force. It turns out that the distribution of stresses on that surface depends on its distance from the middle, or the centroid, or the other terms we'll introduce, such as longitudinal or neutral axis. But let's go on. So this one is just throw in some numbers, essentially. Here's the cross-section, AB. Okay. And here is sigma x. Again, same exact thing we just did. Sigma x now is 1,000 newtons. The cross-sectional area is 1 centimeter by 1 centimeter. We do our dimensional analysis. We get that that's going to increase things by 10 to the 4th, okay, in terms of thinking about meters squared. And we have a 10 to the 3rd with 1,000 newtons, so we get 10 to the 7th newtons per meter squared. And we might write 10 to the 7th pascals, but more likely, as an engineer, you're going to see people writing 10 megapascals. A lot of the stresses, we'll go through some of the typical values, right, in a second, because that was one of the things asked, what are common values. So we'll go through that in a second. But here we're talking in megapascals. Or you might see, if it's not in metric units, you could see things in KSI. So that's kilo PSI, so 1,000 PSI, right? And PSI is pounds per square inch. What if F is equal to minus 1,000 newtons? Well, we don't have to do the math all over again, right? In fact, I guess I already did it. I had just left it down there. It's just the negative, right? It's just the negative of what we have here. Oops, yeah, there you go. Okay. Any questions on this? Okay to go? Not yet. Okay. All right. So here are a bunch of conversion factors. Please do not write these down. Okay. I mean, yes, it's good to take notes, but you got them, all right? So a bunch of conversion factors. The one that I think comes in handy often is 1 KSI is equal to 6.89 megapascals. Yes, it's the last one. Okay, but some of these are just reminders about what the prefixes mean and making sure that we use appropriate ones for them. Now, this is kind of off the wall, but I thought I'd throw it in there. Sound waves. Okay? We're talking about stress, and one form of stress is actually pressure. Okay, and I didn't have time to do it, but when you have pressure, like when you dump or you put a cube into the ocean, right? Remember rho GH is the pressure, right? H being how far, rho 1,000 kilograms per meter cubed or something, you know, and G's are gravity, 9.81 meters per second squared. Anyway, so as you have an object completely surrounded by a fluid medium, the stress is actually going to be the same normal stress on all 6 sides of that fictional cube. And it's pretty remarkable that the pressures, now these are RMS pressures, so they're not exactly peak to peak, right? Root mean squared. These sine waves, and they're compression waves, right? So you kind of have to imagine that between me and you, the air is doing this, going back and forth, okay? And so it's being pressurized and unpressurized. Pressurized, you have positive, well, it's being opened up so that you could consider it to be positive, and, if you want negative, depending on how you look at it. or if it's compressing, that might be your positive, and then when it expands, it's a vacuum, so that'd be negative. I guess that's the better way to think about it. But very small pressures, right? So these are the sounds or some of the pressures associated with just being the smallest or the softest you can hear are conversations and a jet engine. And I think this is a jet engine at 1 meter away. So this is really loud, and yet it doesn't crack a kilopascal. Now, our yield strengths of materials, okay, we will cover quite a bit on criteria for failure, for yielding. But for now, if it's normal axial loading and you have a normal stress and just that normal stress, that is often what is being used to test the materials in a lab, and the yield strength that they post is the resulting stress when you're pulling a bar apart. Okay, so if you have a bar that you're pulling apart, like they did in the lab, you can look at the yield strengths of these materials. So these tend to range, all right, down from a couple megapascals, all right, up to thousands of megapascals. And we are going to be doing a lot with steel. Okay? And one of the cool things about steel is that you can tune its strength. You can tune its strength through either inducing stress and strain and plastic deformation into the material, or you can tune its strength by applying hot and cold to it. Okay. And so it has a very large range. Okay. And then some of these other materials. Do any of you guys have favorite materials that I didn't include here that you wish I had included? Okay, good question. Very good question. I didn't put ceramics on here. Yeah. Well, so Kevlar has to do with the fibers, right? Yeah. So these typically are done in tension. We'll cover this, but materials can behave differently in tension and compression. The metals and a lot of the plastics, okay, materials that are kind of ductile, like they kind of don't just fracture real quickly like glass does, those typically have similar properties for both tension and compression. But the ceramics and the glasses, those will be able to handle more in compression than they can handle in tension. And it's not, how do you say it? It's not suave. It's not nice and easy and soft when it fails. It is catastrophic. In fact, in one of the links I put up there, actually for the online text from Douglas Holmes at Boston University, it's not his YouTube video, but he has on that link, he has this page of videos of what's called Prince Rupert's glass, and it's pretty wild. Okay, it's pretty wild to see how the stress waves propagate so quickly. Okay, anyway, you got me on a tangent. Okay, so axial loading again, and now looking at strain. So strain, normal strain, or strain in general. Strain represents the displacement between particles in the body relative to a reference length. I like this definition. It says, hey, here's a part of your structure, here's another part of the structure. Before you loaded it, they were this distance apart from each other. After you loaded it, they're this distance apart from each other. Okay? Strain is what we can use to measure that deformation. And it's compared to a reference length. Okay, so I'm kind of jumping the gun a little bit. These have no units. They're unitless. Okay? Because it's some change in length relative to original length. So we'll get into how you describe them. But here is our cube again. And we have X, Y, Z. Let's just take a 2D profile. In this case, we're going to take the XY. All right, so you see this is X, that's Y. All right, now we essentially rotated. It's not the best, this went over there, this went over here. Great. And we're going to say, here's a little cube, or a face of the cube, okay? And each one of these has length d something. So this is a dx length, this is a dy length. With normal strain, what happens is we apply some type of force, some type of load to the system, and we look at some deformation. And in this case, we'll say, hey, this wall in this case stays here, and this wall comes over here. And if you go and you look at some of the links I sent, you'll see all kinds of complicated geometry that accounts for translation and deformation. Okay, feel free to use that on your own time and get ready for grad school or more advanced class. Okay, but we're going to keep it pretty simple here. So normal strain, okay, is off the x face, right? So you remember something? This sounds familiar, right? Off the x face in the x direction, right? So epsilon xx can be thought of as, what is this? Delta x divided by dx. And of course, this is greatly exaggerated. At the local level, unless it's a rubbery material, okay, where you have, actually I'll show that in a second, like greater than 10%, some of these silicones can go up to like 900%, okay, strain. This will typically be much, much less. Okay. So a normal strain off the y face in the y direction would be epsilon yy, okay, and be given by this, right? And similarly, epsilon zz would be given by delta z over dz. Since these are normal strains and we have replicate subscripts, we'll just say that they are simplified as saying epsilon x or epsilon y or epsilon z. Now, you could have translation. Okay, so again, if you want to take a look at some of the extra notes, go for it. You can have translation, right, with no strain, right, with no deformation. Okay. That is possible. Okay. And in a second, you can also have shape change with no normal strain as well. Okay, that's what shear strain is going to be, but we'll get there in a second. So let's do another example that's very similar. Okay. What is the normal axial strain in the bar shown? What happens if the axial force is reversed? What are common values for strain? So I left in the force, I left in the cross-sectional area, and we add L equals 1 meter and delta equals 1 millimeter. Do you need these? No. Not if they give you the delta and they give you the initial length. Right, so epsilon xx, which is the same thing as epsilon x, is going to be just this delta over the length. Okay, so this is going right. We were looking at the elemental level, I guess you could say it, right? A material element, and now we're looking at a structure. So again, we can do our dimensional analysis. This is 1 millimeter over 1 meter. Pick your poison, I guess. You could decide that you want to do both in millimeters, that's fine. Or you could decide you want to go to meters, which is not what I did, okay? Either way, it's going to be fine, right? So these, or actually, either way, right? Because they cancel this way or they cancel this way. You're going to get unitless in the end. So this is 10 to the minus 3 for strain, or 0.1%, right? And it was already down here. What if delta is equal to negative 1 millimeter, then we say it's negative. Any questions? We're good, right? This is happiness. So the units of strain are dimensionless. You can find them either in a scientific notation, like 10 to the minus 3. You can find them in percentage. And then there's microstrain. Okay, so microstrain, I guess I should have put 1 microstrain is equal to 10 to the minus 6. Okay, I don't know. Is it worth doing? I'm not going to do that. But 100 microstrain is equal to 10 to the minus 4 or 0.01%. Common values for strain. The alloys, the metals, like steel, aluminum, we're typically talking less than 0.1%. Okay? And so you can already go back and think about what we did for axial loading and say, hey, 0.1%, how much was I, when we're doing those micron measurements, right? So, hey, it's only 13 microns, or it's only 100 microns, or it's only 35 microns, whatever it was. Now you can be like, oh, 35 microns divided by the initial length. What is that strain? Thermoplastics, typically less than 1%. And then the elastomers, the rubbers, often greater than 10%. Can be greater than 100%. Anyone do physical therapy? I've been doing some physical therapy, right? You get those bands. They're pretty amazing. They're pretty amazing. Talking, 100% strain. So there's a guy doing his physical therapy, okay, with those rubbery materials. In our lab, the reason I'm partial to some of these rubbery materials is because when you work with systems that have soft materials in them, you're going to find yourself using some silicones at different times. Okay, shear stress. Shear stress is a stress state where the stress is parallel to the surface of the material, as opposed to normal stress when the stress is perpendicular to the surface. Okay, so, right, sigma ZZ, or sigma Z was our normal stress. There are 2 other components, sigma ZX and sigma ZY. So, we want to be able to describe all 3 of them, right? Because we were interested in describing that traction vector, which was describing the delta force vector, okay? And so our 2 options are sigma ZX and sigma ZY, and we don't write them that way, okay? You'll be more prone to see a sigma 3-1 or a sigma 3-2 than a sigma ZX. Okay, it's just, that's how you can write it that way, but we write it as tau b, and that's just recognizing that is the shear stress. But yes, you can use a different notation if you're using the numbers. Yeah, so you sometimes will see like sigma 1. That's usually meaning in the x direction. Okay? Sigma 2 usually meaning in the y direction. Sigma 3 usually meaning in the z direction. So let's look at a 2D projection of the xz plane. All right, so what is that? So xz, right, this is the x direction, this is the z direction. So what we're going to say is, okay, here is essentially this entire plane on a line. Okay, we just went, there you go. So there's xz, and now, look, it's hard to think about sigma zy coming out at me, all right, but I can think about sigma zx, right, on the surface. So sigma zx, or tau zx, right, is going up. Everyone see that? That was the sigma zx. This is now the tau zx. Now, let's think about equilibrium in the x direction. X is up in this case. Okay, so what do I need to do? I need to think about this tau zx acting on my DAZ, all right, this area here, to give me a force. So the vertical force, the force in the positive direction for tau zx, is going to be tau zx times that dAz. Okay? And wait a second though. I'm now thinking this is a side of one of my material elements. So it was supposed to not be there, all right? But it was going to be suspenseful because this was going to be spinning. Well, how's it going to be spinning? It's going to be spinning like this, right? It's going to be whoop, you know, really positive, happy spinning, okay? Or actually translating first. Oops, I can't keep my thing straight. It was going to be translating first. Okay, it's going to be translating up. But we need something to keep it from translating up. So why don't we put another force associated with tau minus z minus x, right? So this is the minus z face, and this is in the minus x direction. So I put that minus tau minus z minus x dAz, and that's going to be equal to 0, right? So now it looks like I've got this element not accelerating in the vertical direction, okay? But now we have another issue, okay? Okay, and tau zx is equal to, let's look at the moments. And to do the moments, we have to think about what are lengths, right? So these are forces that are acting at some distance, and this is going to be my reference point. Again, it came in too early. So here's the reference point. Here are these lengths. Here's a shear stress, and there's a shear force associated with that shear stress. Okay? So then I start summing up, right? And y, the moment y, that's coming out of the page at me. So what am I going to do? I need something to compensate for that. Okay? Something to keep me from spinning. So I've got this one now. All right? So I could say, all right, now I have a tau xz. All right, this is good, right? So now that tau xz, all right, and why is that tau xz? Because this is the x face in the z direction. Is this confusing yet? Yes. Right? Okay, it's okay. It's the first time. Okay? First time. And by the end of the semester, you won't care about this derivation. You're just going to know, I draw the arrows this way on this box, and then I'm happy. Okay? That's all you're going to think about. All right? But we're just showing that, yes, this box does not rotate and does not translate. But look, if I crank this tau xz enough, okay, I can keep it from rotating, but now the box wants to translate to that direction. It wants to go to the right. Okay? So what do I need to do? We should note that the dAz times the dz and the dax times the dx, or times the dz, sorry. These are the same thing. Some people will just do this in terms of x, y, and z, okay, for the different lengths, different sizes. And so what you end up getting is dx, dy, dz, okay, for these terms. I'm going to add another stress, another shear stress to keep us from going right. We want to stay with zero acceleration. Okay, I guess we could have constant velocity, but we want zero acceleration this way. Okay, so what we're going to do is we're going to add another this other shear stress, and we're going to say the forces have to be equal to 0 in the z direction, and we're going to get that this tau minus x minus z has got to equal the tau xz. Okay. And this is where we are. So this is exactly what the result is. Okay, that tau zx is equal to tau xz. Tau zx is equal to tau minus z minus x. Tau xz is equal to tau minus x minus z. What does that mean? It means that all of these shear stresses are the same value, okay, in terms of them being scalar. Okay, but we draw them, and they're drawn this way. Okay, this is a This is the convention, okay? Right side up, okay? Top to the right, okay? And then you can, once you get those two, okay, then you get the other two as well, okay? And this is the convention for positive shear stress. If we then say this is just one face of the whole cube, all right? What do the other faces look like? Okay? So remember, this is a tau zx, all right? All right, so this is coming out of the z, all right? Okay, so here's the tau zx now over here, or tau xz, right? They're the same. Okay, they're the same. So the same convention applies. This is the face, this is the direction. This is the face, this is the direction. And so now we have all these shear stresses potentially, all right? You know, they can be zero, right? But we have all these shear stresses acting on the different faces. Any questions on this? This is not trivial, okay? Not trivial at all, in my opinion. So, shear strain, once again, there's the outcome. This is the same element we've been drawing, okay? So it has an x, a y, and a z. And we have dAx, day, daz. And if we take now a 2D profile, right, of the xy plane like we did before, we can get what we had here. This is exactly what we did for the normal strain, okay? But shear strain is going to do something kind of wacky. Shear strain is going to cause a shift in parallel surfaces. So shear strain is a deformation of a material substance in which parallel internal surfaces slide past one another. Right? Anyone taking fluids right now? Right, there's lots of shear stress that you talk about there. Okay? That's viscosity, okay, that you're dealing with, right? It's related to the often we measure viscosity in terms of the force required to move two parallel plates with the liquid between it. Okay, that's how you measure viscosity. So this is shearing like this. This has dx. Notice, like we just said, this bottom length did not change. This top length did not change. So the normal strains for this are 0. Okay, because this dx, there's no change. But something has happened, right? We know that there's now a different shape here. So we have a delta here and a delta here. Blow it up, okay? And what are we going to use to describe our shear strain? We're actually going to use this angle right here. Okay. So this angle is going to be what we use for shear strain. The tangent of this angle, right, is this delta divided by dy. And we can use a small angle approximation and say it's just delta over dy. And we report shear strain as gamma. Okay, gamma xy. What did I say here? Did I say this is delta? I meant this is gamma. All right, I say the wrong thing often. This is gamma. Okay. Okay. So shear strain hold on, I don't know why it's sorry. Okay, it's the same thing. Sorry. Okay, I did something. All right, so we've covered shear strain. All right, and we'll cover how to calculate shear strain based off of shear stress soon. Okay, but this is just the definition of what shear strain is. Finally, the last slide. We can describe the general state of stress with 6 components. 3 normal stresses, 3 shear stresses. Okay, we may have gone through this a little fast, right? But tau xy is equal to tau yx, and tau xz is equal to tau zx, and tau yz is equal to tau zy. Okay, and so you have 9 possible combinations here, but a lot of these are repeats. Okay, now the tensor, which we'll talk about in a second, still keeps those repeats in there. Okay, but a tensor is a number or a collection of numbers that maintains its meaning under transformations. So in other words, we've described stress at a point, and we have this like beautiful sigma x, sigma y, sigma z, tau xy, tau xz, tau yz. We have all these 6 components of stress. Well, what do? We say, I'm just going to rotate my cube a little bit. I'm going to leave it at the same point, but I'm going to rotate it. You're like, why in the world do you want to do that? Well, sometimes the state of stress is more conveniently described at a different orientation, right? That's like, how do you pick your Cartesian coordinates, right? This is like, how do you pick your orientation for your material element? So a tensor means it's a number, or it's a collection of numbers that will tell us the same thing. We don't lose information when we do a rotation. That's all a tensor is. And there's a great video by, I guess, the Science Asylum guy. Okay. So all we want to do here is say, look, I know that I can have normal and shear stresses on my cube. Okay? And I have described them now. This is normal stress, these are shear stresses, right? This is all I did was I took that shear stress diagram and put the normal stresses on it. We're not showing the stresses on the hidden sides. Yes, that's true. And what a tensor is, okay, is saying it's a form of describing that state of stress completely. Okay? That's all it is. And it is, remember we said we had these traction vectors as well, okay? But we can describe the state of stress on this element, and we often do it in terms of a matrix, okay? A matrix is not a tensor, right? But a matrix, or a matrix can be a collection of numbers that does satisfy this tensor property. And the last thing here is that instead of writing sigma 1, 1, sigma 1, 2, sigma 1, 3, I can write these. These cross terms are the same. These cross terms are the same. Tau xz and tau zx. And in a little bit, we'll show you how to use these. Okay? But this is just giving us a general depiction of the state of stress. So that's it. If you have any questions, let me know. We will have an in-class, well, the in-class assignment is posted, and the the non-in-class one, all right, that one will come up a little bit later today, all right? Thanks, guys. We went a little bit longer because there was questions at the beginning, right? We did some question and answer at the beginning, so, but we're all good. Have a good one. You too. Thank you.
I was added to the class last night, so I didn't have access to the Canvas until this morning.
Okay, all right. So please send me an email, and I will extend the deadlines on all the assignments.
I can try to do most of them tonight, but I'll put in the email.
Well, no, I think you got a lot of catching up, so we can extend it for a few days. But people are asking me for extensions, and they're not sending me emails, and I have no idea who's asking. So you got to send me an email. I can't give extensions without emails. Your name is? Tahare? Okay, good to meet you. All right, yes.
My name's Riley.
Okay.
So I know we have our test in about a month.
Yes.
And I was just wondering, like, how would you recommend, like, getting ready for that? Because I know we don't have a textbook, so it's kind of hard to come up with.
So I'm gonna post the 4 semesters of previous problems.
Okay.
On exams.
Okay.
And that should be pretty good.
Like,
okay?
Is it just like comprised of like the questions we do in our assignments? Is that?
No. So that's why you guys we're gonna need to spend time. No, these assignment questions have been like 1-to-1. All right.
Yeah.
What happens on the exams is you gotta do, like you're seeing, right? You gotta do equilibrium.
Right.
So then you can calculate the internal force. So then you can calculate the stress, right? Once you calculate the stress, is it going to break or not? Right? So there's like these things.
Drawn out.
It's drawn out. So
Okay.
we're laying the. I mean, I understand people want to do practice problems,
Yeah.
but in the past, people have also said that the problems from the book are not representative of the problems on the exams.
So it's not worth it.
So
Okay.
you
Yeah,
can do.
I'm just getting nervous for it, so I just want to know like what I should do.
So you can pick up. I mean, I think Hitler's book is great. So you can pick up Hitler's book, and I would say, look at the examples
Okay.
in the chapters to get you
like
know.
that's a more
that's-
accurate depiction.
I think
of the test
because
paper.
you'll see. I mean, and then you'll have, and then look at the exams. Okay, look at the exams, and don't freak out. There's going to be time. I think I will also probably temper the exams a little bit, so they shouldn't be as wild
Okay.
as they've been in the past, based on the type of style that we're going for.
Okay.
But it's conceptual. Okay.
It is.
It's conceptual, so you're never going to see the exact problem. Okay. At least that's, it's not. It's going to
Right.
be, all right.
Okay,
Here's
yeah.
a variation on a theme. Okay. Now I can't outdo myself every time, but if you with 4 semesters of proms, you get an idea of what
Right.
the way I think about things.
Yeah. Okay. All right.
All
Thank
right.
you very much.
All right. Good luck,
Enjoy your
Riley.
weekend.
Yes, you too. Yes. Right now.
So they're both in millimeters?
So, this is in millimeters. Oh, I need to change that. It's supposed to be meters. It's in meters. It's in meters. Let me just change that real quick.
Just multiply that quotient by like 100 to get the percent, or?
You got to do the right. Yes, I mean it's going to be a percent, right? So it's going to just be it's going to be the quotient. So it's going to be, in that case, it was what 0.1 millimeters over 1,200 millimeters.
So you just multiply the by 1,000
By 100.
It doesn't.
Oh, to convert first.
Yeah.
I mean, to change it into percent, then by 100.
Yeah. So then you got to get it. You get a dimensionless number, right?
Yeah.
And then yes, you have to multiply by 100.
Thanks.
Okay.
Thanks.
So all right.
Also, I want to let you know that when you posted the complete slides, you didn't have any notes on it.
I didn't.
So it's just blank for everything.
It's just blank.
You just had all the slides, but nothing written on it.
What in the? How did that happen? I did a save as. Okay, well it's my fault. It is what it is. So thank you for letting me know that they're blank. I didn't know that the slides were blank.
So
Yeah.
they don't pop up? Oh, so was it purposely blank?
I was supposed to be complete.
Oh, okay.
I'm sorry. I meant to make them complete. Guys, tell me when this stuff happens so that I can try to check. I can check it at the beginning. Say yeah. I didn't know.
Have a good weekend.
You too.
In the in-class assignment, is this supposed to be 1.66 meters or millimeters?
Huh?
Your
What's that?
initial length of 1.6 meters or
1.6 meters. I'm changing that right now. I'm gonna change it. I'm
Yep.
sorry. That's my
No,
badness. Multiple badnesses. Yes.
So I was doing homework from last time,
Uh-huh.
and then number 4. I know that it's pretty the same as another one on the homework, but I guess I'm missing out the units, so that's why I'm getting the answers wrong.
Okay.
So is there a way we can go over it?
So yeah, I mean that's a good one to do in office hours because
Okay. It's,
no one else is not many everyone else. When there's a question like that, we can go through it. I mean, what I'll say is that the collab, if you just ran the collab and put in the new numbers, you get the right answer.
So this is the thing. So I could do that, but I feel like I'm like cheating the system, kind of. Like, okay, so if I did not do that, I wouldn't really get it right. So I'm basically just copying it.
Okay.
If that makes sense.
It does make sense. It sounds
So-
like it's a little painful, but sure.
I'm so
No, so I mean that's fine. I just gotta add this
If
unit.
I know it's in the office hours in like 30, 20 minutes.
Yeah.
So would that be better if I just wait?
Yeah, or we can talk about it right. Let's see. I should get over there. So I have office hours over Zoom. So if you want to meet over Zoom in like 20 minutes, that would be fine. So I can get there on time.
Okay.
And then you can do whenever. Or, I mean, it should be quick. If you have it, do you have the work right here? Maybe I can just take a
Oh,
look.
I do not. I think I do. Or if is it fine if I email it to you? And
That's,
you can like point out what is the circle
Um,
there. Be
I
like,
mean,
this is
yeah,
right.
that's fine. How do you say it? I think it's faster. Oh, I didn't stop. It's still going.
It's not bad.